You know that feeling when the power goes out, right? 1 second the lights are on, and the next, poof, you're in the dark. But when a massive blackout hits, one that affects millions of people, it doesn't just happen. No, it spreads. It spreads like a virus through the grid and with absolutely terrifying speed. This number you see here? This isn't just some random statistic. This is a countdown. During that huge winter storm back in 2021, this is how close the entire state of Texas was to a complete and total grid collapse, 4 minutes and 37 seconds. And a collapse on that scale, well, it's not something you just fix in a couple of hours. We're talking about a blackout that could have taken weeks to fully restore. Weeks! Imagine millions of people with no power, critical equipment damaged. It would bring modern life to a dead stop. So you have to ask, how does a system get to the brink of disaster that fast? And that's the real question we're digging into here. It's almost never about just one thing breaking. It's about how that one single failure can light a fuse, triggering a chain reaction that brings down an entire interconnected system with truly shocking speed. So, how does it work? Well, the answer lies in a phenomenon that engineers have a very specific name for, but for the rest of us, it's probably better known as the domino effect. Okay, so the official term is a cascading failure, and it's exactly what it sounds like. It's a chain reaction where one small piece failing doesn't just stay a small problem. Instead, it triggers the failure of its neighbors, which then causes their neighbors to fail, and the problem just grows and spreads almost exponentially. Let's break it down real simple. Imagine one big, high-voltage power line goes down. All that electricity it was carrying has to go somewhere, right? It doesn't just disappear. It instantly tries to find another path, jumping onto nearby lines. The problem is, those other lines might already be running close to their limit, so this sudden surge pushes them over the edge, and they shut down to protect themselves. Well, now you have an even bigger amount of electricity looking for a home, and the failure just keeps spreading. It's like a ripple in a pond, except it's moving at the speed of electricity. So why is the grid so vulnerable to this kind of cascade? To get that, you really have to understand the fundamental and incredibly delicate balancing act it's performing every single second of every single day. Here's the absolute core challenge. Electricity isn't really something you can store in the grid, not like water in a reservoir. The amount of power being generated by power plants has to perfectly, and I mean perfectly, match what everyone is using at that exact same instant. It's a constant, real-time tightrope walk. So what happens when a big power plant or a major line suddenly goes offline? Well, your supply instantly drops, but the demand from everyone's homes and businesses stays high. The whole system starts to slow down. The frequency of the grid, which is normally held super steady, begins to fall. It's a lot like a car losing speed when you suddenly take your foot off the gas pedal. And as the grid operators try to fix this imbalance, telling one plant to ramp up, another to cut back, the system can start to swing back and forth wildly. A user on Reddit actually put it perfectly. It becomes like a truck that starts fishtailing on ice. The more the driver frantically tries to correct it, the bigger and more dangerous the swings become. Okay, so that's the theory behind it all. Now let's take a look at how these principles came together to create a real-world catastrophe. We're going to dive into the huge 2003 Northeast blackout. This was an event that knocked out power for 50 million people across the US and Canada. And really, it is a textbook example of a cascading failure in terrifying action. So what was the initial spark that lit this massive fire? It was something almost comically simple. It was a hot day. Power lines were carrying a heavy load, which makes them sag, and a few of them sagged just enough to touch some overgrown trees below them. That caused a short, and they automatically tripped offline. Now, that should have been a small, manageable problem. But here's the kicker. There was a second, hidden failure. A software bug in the control room's alarm system meant that for over an hour, the grid operators were completely blind. They had no idea that the first few dominoes had already started to fall. Just look at this timeline. At 2:02 p.m., the first line trips. Okay, not a catastrophe. More than an hour goes by, and at 3:05, another one goes. The system is definitely getting strained, but it's still holding. But now, watch the clock after 4 p.m. At 4:05 and 57 seconds, a really critical line trips. Just 37 seconds later, the cascade truly begins. Lines start tripping out all over Michigan and Ohio. And then, a mere 9 seconds after that, the international power lines connecting the US and Canada start to fail. In less than a minute, a problem that had been slowly simmering for 2 hours exploded into a continental crisis. So when the grid is fishtailing totally out of control and the dominoes are falling faster than you can count, how do you even fight back? I mean, that is the terrifying question facing people in the control room. When a failure is spreading this fast, what can you possibly do to stop it? The main weapon they have is something called load shedding. And it sounds completely backward, but sometimes the only way to save the entire system from completely destroying itself is to intentionally start cutting power to some people. These are those planned rolling blackouts you hear about. They're like surgical cuts designed to relieve the pressure and stop the cascade in its tracks. And load shedding is just one of the tools. There are automated systems that can sense that dangerous drop in frequency we talked about and just start cutting load automatically. Operators can also trip entire power plants offline to protect them from the wild power swings. Or they can do something called islanding, basically intentionally isolating the healthy parts of the grid from the parts that are failing, kind of like building a fire break in the middle of a raging forest fire. But all of these measures, they're part of this unbelievable race. The problem itself, that power overload, is moving through the wires at nearly the speed of light. And the control signals that are trying to stop it, well, they can't move any faster. It's this desperate, split-second race against the very laws of physics. Which really brings us to the final thought, doesn't it? The power grid is the most complex machine humanity has ever built, and our reliance on it is only getting bigger. Understanding just how fragile it is and the terrifying speed at which it can all come apart isn't just some engineering problem. It's a question we all have to face as we keep building our electric future.